What is the natural algorithm in its derivative? The natural algorithm is ln of x, which is defined as the nth square root of x minus 1, and that repeats itself n times, and we do it many times for increasing n, and at some point we get the natural algorithm of x. The question is, what is its derivative? What is the derivative of x? And the answer is, it is actually 1 divided by x, when x is in R. But why is that? How can we prove this? The fact is that we have the Euler number, the e, and we can form this expression e to the x. And then we have this expression ln of x, right? And these two are related. But now, how can we prove that the derivative of ln in relation to the x is actually equal to 1 divided by x? So why is this true here? For every x that's a real number but greater than 0. So we can insert here a number that's greater than 0, like 1 or 2 or 3 or pi. So what's the question? What's the answer here to this question? Basically, we just look at this other expression, which is e, and then we put in here not x anymore, but ln x. We put ln x in there. And we know that basically if we choose this x to be greater than 0, so we can actually insert it in this ln, then this will be equal to x. It's the same. So these two cancel each other actually out. And then we have this x equal to this x. And now let's take the derivative on both sides. So we look at the rate of increase of change of x at this rate on both sides at the same time, on the left and on the right. So what happens? So let's just denote the derivative like this. So we're gonna derive this rate of increase, the derivative basically on both sides at the same time, like this. All right. So what's the derivative of x? Like if you have the function x is always just x. The rate of increase is always the same. It's 1. And what's the rate of increase here? And here we're just going to use the so-called chain rule. And basically the chain rule is applied at 2 places. So at this point we're going to separate it, and we say that e of something is a function and ln of something is a function. And then the chain rule says that you have to take this e and then take the derivative of this e, and then leave the ln x as it is. So this is just a separation that I drew in here, but this is the actual derivative apostrophe, just like here. All right, and then we take this times the derivative of what's inside the chain, and that's the ln. There you go. There we got the derivative here. Just like this is the expression that you want to figure out what it is. And now here it says ln apostrophe, so the same expression, and then the x stays the same. And that's what we got. And now we look at the equal signs that we have. We got equal here, so this one, we start equal this, whatever it is, equal this, whatever it is, equal this, equal 1. So this 1 is actually equal to this stuff. So how come? Why is it? Well, we just proved why, but this is now a fact that we're gonna accept. So let's write this down one more time. So actually it's 1 equal e apostrophe ln x times ln apostrophe x. All right, and now the derivative of e apostrophe whatever this is is going to be exactly equal to the same. It's just E ln x. This one doesn't change. But this, as we stated earlier somewhere, is equal to x. You see where we're going with this? And so that's why this whole chain of statements here, we can again reformulate and say, actually, this is just the one, this equal again, and now it's the x times, and then everything stays the same. Apostrophe x. And now this, of course, is if the x here is greater than 0, which it is, it's a real number, we can just say divided by x, both sides of the equation. So here we got 1 divided by x divided by x is 1, so you can just leave it out, and then we get the ln apostrophe x. And that's what was to be proven.